In lecture 13 of particles, symmetries and fields, we're going to give you an example of these metrics of the killing forms. We'll give you a non-degenerate example and a degenerate example. And it turns out that there are some special bases called adapted bases, which means that we can have a nice simplified notation for the structure constants. Then we're going to construct some Lie algebra operators which commute with all other elements of the Lie algebra. They're called Casimirs, and they're useful because they label the eigenvalues of them label the different representations. Then we'll talk about the decomposition of Lie algebras and Lie groups a little more. We'll bring that along. And then finally, we'll get on to complexification of Lie groups. Okay. So let's give an example of this metric of the killing form. So first example we're going to take the Lie algebra of SU2. Now 6.1 tells us that our metric of the killing form kappa AB is the trace of the adjoint matrices of A and the adjoint matrices of B, we've looked at these. We found adjoint representations, so these a basis for these adjoint matrices before, and it was just -1 times epsilon basically. So this gives us epsilon ACD. In fact, let's write it like this: A, D, C, epsilon B, C, D. Okay, so this is equal to -2 delta AB. So this, no matter which two vectors XA and YB we multiply this by, as long as they're non-zero, we're guaranteed to get a non-zero answer. So this is non-degenerate. Note that if we'd have chosen physics conventions, we'd have had a couple of factors of I in here. Because we absorb some factors of I, and one gets +2 delta AB. Of course, if you take a different basis, you will get a different value in front of the delta, Kronecker delta. So there's a non-degenerate example. For a degenerate example, let's take the Lie algebra of the isometries of a two-dimensional plane. So we have two translations, and there the algebra elements are E1 and 2, and we have a rotation. We'll call this J3. So the Lie algebra is J3 Lie bracket with J1 gives you E2. With E2, E1 gives you E2. J3 Lie bracket with E2 gives you -E1. And the Lie bracket between the two translations is 0. So from the Lie algebra, we can read off the structure constants. The only non-zero structure constants are F231 is 1, is minus F213, and F321 is minus 1. This is from the second Lie bracket, which is minus. Of course, we've got the anti-symmetry on the final two indices of the Fs. So remember that before we derived that FCAB is equal to the adjoint, or we can set it equal to the basis adjoint matrices, the C-Beath entry, so C-th row and Beath column. And so just plugging in the structure constants here, we see that we can write the adjoint matrices. So T1 is the adjoint matrix corresponding to E1, and this one has zeros everywhere. There's a minus 1 there. T2 adjoint is 0, 0, 1 with zeros elsewhere. And T3 corresponding to J3 is 0, minus 1, 0, 1, 0, 0, 0, 0, 0. Okay. So what all this means is that our metric kappa AB, which is the trace of TA adjoint, TB adjoint, is, well, you can calculate it from these matrices, and you get zeros everywhere apart from T3 adjoint squared, the trace of T3 adjoint squared. So you get minus 2, 0, 0, 0, 0, 1. So we've shown that this Lie algebra is degenerate. And therefore, it's not semi-simple. It has an abelian invariant subalgebra, and of course the abelian invariant subalgebra is precisely this one between the two translations. So, okay, fine. So if we look at this first example, here we've got a killing form metric, which is proportional to the Kronecker delta in the particular basis that we took. And any case which is like that is called an adapted basis. So any basis for which kappa AB is some number times delta AB. So like the Lie algebra of SU2 example above. So this is called an adapted basis. So by, even if you originally get something which isn't quite a delta function, you have some other non-zero numbers which don't look like a Kronecker delta, you can rescale the basis vectors such that you do get a Kronecker delta. So it evidently exists for all non-degenerate killing forms. In other words, semi-simple Lie algebras. So in an adapted basis, the killing form of TA, and in the second argument we put the Lie bracket of TB and TC, Well, this is equal to, since the Killing formula is bilinear, this is equal to kappa of, so we use the Lie algebra here as well. So we have kappa of TA and TD. Because we're in an adapted basis, this is equal to kappa FD BC times delta AD, which of course is kappa F ABC. All right, so that's one relation. We also have, by a completely analogous argument, that kappa of TA comma TC, with TC in the second, TB, that should be TC in the second argument. So similar, absolutely analogous argument gives us this C kappa C. Now, invariance property says that these two left-hand sides are the same, and therefore the right-hand sides are the same. And so when we have an adapted basis, we have the equality of these two structure constants. Okay, so just by cycling the indices, we can show that this is also equal to FBCA. And we also have the fact that, if we switch the last two indices, we have anti-symmetry. So we have minus FACB is minus FCBA, which is minus FBCA. So we have this total anti-symmetry under switching the indices, and in fact it's common in this case to write them all downstairs. And so we put ABC is defined to be FC upstairs with C upstairs and AB downstairs. And so now the FABC are totally antisymmetric. This is what we've just shown in the adapted basis. And the Lie algebra is written TB is FABC TC. Good. All right. Now let's define a new object, which we will find useful, and it's called a Casimir operator. So a Casimir is a Lie algebra operator that commutes with the Lie algebra. So for a compact group G, okay, so let's take a semi-simple compact group G. Remember, we defined compact way back to be having a finite group volume. So, for example, SON and SUN, these things that look like generalization of spheres or whatever, they're compact, but the pseudo-orthogonal and pseudo-unitary groups are not. So in particular, for example, the Lorentz group SO1, 3 is not compact. But for a compact group, which is semi-simple, so there is and there's an adapted basis. Oh, I beg your pardon. I should have told you that first. Let me do that first, actually. Right. So okay, so I'm going to talk now about these compact groups. Let me do that first. So compact groups have a finite group volume group manifold, e.g. SON, SUN. Non-compact groups examples are pseudo-orthogonal or pseudo-unitary groups. So if you have a compact group with a degenerate killing form, this implies an abelian invariant subalgebra since, because it's degenerate, we have, you know, the killing form of some elements of the Lie algebra is 0, which implies that for some A at least, T adjoint is 0. So this commutes with all elements of the Lie algebra. So for this compact case, this compact degenerate case, the Lie algebra, let me just say that, compact degenerate case. The Lie algebra can be composed into a direct sum of a semi-simple part and an abelian part. So, like, for example, what that means for the groups. So you can have your overall group G could be some semi-simple part, which of course, as we showed before, is a product of some simple parts multiplied by some abelian parts, and there could be several U1s. And in general, you can have a coset with respect to F. So with so there's a U1 factor for each zero adjoint. Each XA times T8 adjoint is 0. So F is some finite group. It's finite group within G. And F could be trivial. You don't have to have a coset. Okay, so we're beginning to see some categorization of Lie groups come about here. Certainly compact ones. So if it's degenerate, we get some U1 factors. And if it's not, we just have the semi-simple part. All right, now I can go on to Casimir's. So a Casimir is a Lie algebra operator that commutes with all of the Lie algebra. So for a semi-simple compact group, there exists a quadratic Casimir we're going to call this C. So this is TA. So we're going to choose a convention here for the basis, or well, actually not for the basis, for these TAs. The convention here is that TA is defined so that we have an adapted basis. We know we can have an adapted basis because it's semi-simple, so it's non-degenerate. So kappa AB is and it'll just be minus delta AB. So the constant proportionality is -1. Now, we must check that, okay, so we've got to check that this operator that we've defined actually does commute with all elements of the Lie algebra, and it's sufficient to check that it commutes with any TB. So the Lie bracket with TB and C is equal to 0. Since then we can just multiply by some XB and we get the result. So TB, C, well, the Lie bracket is such that we just substitute in for C. And I can write this commutator as the sum of two terms. And I can write it like this. And the additional terms that we get from the Lie bracket just cancel between the first and the second terms. And of course, the reason we've written it in that form is because we can use the Lie algebra to calculate these Lie brackets. So this is equal to TA F BAC TC. I'm using this adapted basis form of the Lie algebra plus F BAC TC TA. So I can write this. So remember the F's are just some numbers. So I can pull that out of the front, whereas these TAs and TCs can be represented by matrices, and so they don't necessarily commute. So what I'm going to write here is TATC, where I've used this notation for the anti-commutator, for the anti-commutator, TATC plus TCTA. Now, the anti-commutator is symmetric in A switching with C, whereas here we have a symbol, the structure constants, which is anti-symmetric in A with C. So the result is 0 through symmetry of A and C switching. So indeed, we've proved that this operator is a quadratic Casimir. Quadratic, of course, because it's just the product of two of these basis elements of the Lie algebra. So we consider now consider some Casimir in a representation of the Lie algebra. Representation little d of the Lie algebra. So we have, we're going to put suffix d, and this is defined to mean d of TA, d of TA, where of course A is summed over. And so this is a square matrix. It's got, you know, whatever the dimensions of D are in it. And we can use the same, essentially the same proof as above. To show that d of x acting on CD, the commutator Lie bracket with CD is 0 for all x in the Lie bracket, in the Lie group. So here we have Casimirs of representations. Right. So we're going to make a claim now. And there's an exercise in the book which takes you through this claim. So if D is an irreducible representation, then by Schur's lemma, CD, so let's call this big C. Big C is the matrix, is equal to little d times the identity matrix. Sorry, little c d times the identity matrix, where little c d is just some real number. This is essentially what Schur's lemma tells you, and so you see the exercise for the proof. It's about looking at the eigenspaces of this operator. So the thing is, CD can be used. So the Casimir of a representation can be used to label different irreducible representations. And that's because we can make these ladder operators out, from combinations of the TBs, but because they're linear combinations of the TBs, they're also going to commute with this Casimir of the representation. And so if we arrive at different states, they all have the same Casimir. So that's why, every state in the irreducible representation has the same value for this. It's essentially because of this identity matrix here. But between the different representations, the values will change. So let's give an example. So consider the fundamental rep of SU2, the Lie algebra of SU2. So the adapted basis, remember, we write this in terms of the Pauli matrices, sigma A, typically. And normally we have this, but we put an extra square root of 2 on the denominator, and that's to get kappa AB is minus delta AB, which is what we need for this definition of the Casimir. This is our convention. So then our Casimir operator for j equal to half, which of course is TA, is minus an eighth sigma A. And if you look at sigma A, it's 3 times the 2 by 2 identity matrix. And so we identify the Casimir of the j equal to half rep to be this constant in front. So little c of j equals a half is minus 3/8. So more generally, consider angular momentum angular momentum operators J. So they have the Casimir operator being -1/2 J squared. And so this implies that the eigenvalue in the spin J representation is Cj is -1/2 times the eigenvalue of this big J squared, which we know from physics is J times J plus 1, where J, little j, is the total spin. Good. All right. Now, so we made this statement, which we were a bit loose with before. So an adapted basis exists for any semi-simple Lie algebras really only applies to real Lie algebras. And of course, these are the ones that we've been looking at on the whole. This is the span over the real numbers of the Lie algebra basis vectors. And so, okay, so we can define the complexification of a Lie algebra and it's the same thing. We denote it as LC of G, and this is the span over the complex numbers of our basis vectors. And okay, so the original LG is known as the real form of the complexified Lie algebra. So let's give more examples just to bring this out. So our real Lie algebra of SU2, span of over the reals of our basis matrices, which originally we had it in this this basis, which was -I/2 sigma A, where A is in 1, 2, and 3. And these give you all 2 by 2 traceless anti-Hermitian matrices. And remember that when we had the Lie algebra of SL2, C, this was, oh no, sorry, I beg your pardon, jumping ahead of myself. So if I look at the complexification of this Lie algebra, well, of course, it's the span over the complex numbers of the same basis. So these are 2 by 2 traceless complex matrices. The set of all of those. Now, if you remember that the real Lie algebra of SL2, C was actually the same thing as this set of all 2 by 2 traceless complex matrices. In other words, we see that these two things are the same. So the complexification of SU2 is the Lie algebra of SL2, C. So there's a theorem which we won't prove, but it's really about, well, it's about the existence of these adapted bases. So every complexified, semi-simple Lie algebra has a real form which has an adapted basis. Okay, so that's the correct theorem, form of the theorem, being a bit more precise about things. Okay, so now we want to go back just in the last part of this lecture to the way that we analysed the irreducible representations of the Lie algebra of SU2. And we labelled states with the eigenvalues of diagonal generators, and otherwise we constructed a basis using these ladder operators, or these step operators, these raising and lower ring operators. We call them E plus and E minus. And this analysis turns out to be useful for other groups. And the basis that we use in general is this basis called the Cartan Vial basis. So we're going to start developing analysis of general groups, Lie groups, I should say. And so we're going to define this Cartan Vial basis. Okay, so I need to make some more definitions. So we say that an element of the Lie algebra is ad-diagonalizable if the adjoint representation corresponding to X is diagonalizable. So a Cartan subalgebra so I'm going to, it's a bit of a mouthful and it takes a long time to write. So I'm going to shorten this to CSA. So a Cartan subalgebra, L of H. So you have a subalgebra of the Lie algebra. So this is a maximal abelian subalgebra. And it contains only ad-diagonalizable elements. So in particular, we have three properties. So H is in the Cartan subalgebra, okay, means that H is ad-diagonalizable. If we have two different members of it, H and H prime in this Cartan subalgebra, then their Lie bracket is 0. Of course, if we represent them by, well, we'll see diagonal matrices, then obviously the Lie bracket is going to be 0 of the representations. And 3, if X in the Lie algebra is ad-diagonalizable, and the Lie bracket of between X and H is 0 for all elements of the Cartan subalgebra, then X must be in the Cartan subalgebra. So all possible choices of the Cartan subalgebra have the same dimension. It's a maximal choice. And this dimension is called the rank of the Lie algebra. So in what follows, we're going to call this rank R, little r. So for example, suppose our Lie algebra is a complexified form of SU2. So if you remember this, we had 3 elements of the Lie algebra. H, so this is ad-diagonalizable. But E plus or minus are not ad-diagonalizable. So we can choose the Cartan subalgebra to be the span over the complex numbers of this H to be the Cartan subalgebra, and so the rank R is 1. So more generally, if we're given a Cartan subalgebra, we can choose some basis. So let's give you another example. Let's take the Lie algebra to be the complexified form of the algebra of SUN. So this is the set of all traceless complex n by n matrices. So the diagonal elements are a natural choice for the Cartan subalgebra. So in particular, we can choose HI alpha beta is delta alpha I delta beta I minus delta alpha I plus 1 delta beta I plus 1, where, okay, so we have no sum on I there. And Okay, so if you think about it, I has to go from 1 up to n minus 1, because we've only got n by n matrices. And alpha and beta go from 1 up until n. So this traceless condition means that the rank is n minus 1. Okay. So that's the end of the example. So if the Lie bracket of two elements of the Cartan subalgebra is 0, like we're saying, then what this means is that the adjoint representation corresponding to HI has a 0 Lie bracket with the one corresponding to HJ. So the HI are simultaneously ad-diagonalizable. So we can discriminate two types of eigenvectors in the Lie algebra. Of eigenvectors. Those with eigenvalue 0. These are basis vectors of the Cartan subalgebra. And since the Cartan subalgebra is maximal, all remaining eigenvectors must have non-zero value eigenvalues. So these are called ladder operators. Well, there's lots. These are called, so there's lots of different names. So as we called them before, it's raising, lowering operators. This can be called step or ladder operators as well. I mean, they're all synonymous, these three things. And so we denote these E suffix alpha, where alpha is a vector. Well, it's a list of numbers. Complex numbers. So alpha is alpha 1 up to alpha r, such that the Lie bracket of HI with E alpha gives you alpha I E alpha. This is equation 6.2. So this defines what the alpha I are once you've defined the Lie algebra in terms of the H's and the E's, these ladder operators. So a bit of nomenclature here. Alpha is called the root of the Lie algebra. And the set of all of these E alphas is the root set of the Lie algebra. So we'll call this big phi is the set of all E alpha is the root set of the Lie algebra. Okay, so next time we'll go on to develop all of this a lot more in the Cartan bar basis.